Greetings to you. Welcome to Physics with Ben. In today's video, we're looking at how to derive Kepler's third law of planetary motion. The law states that the square root of the period of revolution of planetary bodies is directly proportional to the cubes of their mean distance from the sun. Yes, I want to use a wire equation to derive this law. There's a question this year, question number 8C, 2021, wire question 2021, question 8C. It reads, a satellite of mass small m, a satellite, let's look at this as the Earth, and this is that satellite, and this is the radius of the Earth. This is your R. A satellite of mass, and this is mass of the Earth, capital M. A satellite of mass small m orbits the Earth. Orbits the Earth. Orbits the Earth, orbits the Earth of mass capital M with a tangential velocity small v and with a radius capital R from the center of the Earth. Derive the relationship between the period t and the period t of the orbit in R. Derive the relationship between R, t, and R. WAEC were simply asking their candidate to derive Kepler's third law, and it was hidden in this question. Solution. So let's start. Solution. Recall in the other video where I did on gravitational field that I was talking about the physics of cut and join. That physics will help you derive this equation. Now, this is under circular motion. It will interest you to know that every equation you know in circular motion in your SS1 physics or Year 1 physics, other schools call it Year 9, Year 9, Year 10, Year 12. Your physics in Year 9 or your physics in SS1 has some equations under circular motion. That when a body is orbiting a circular path, is orbiting about a circular path, the body orbits with a centripetal force or centripetal force. And that force is given as what? F is equals to mv squared all over r. In this case, let's say capital R. And let's call this equation number 1. Again, the body moves with a tangential velocity and also what? An angular what? Velocity. And there is a mathematical relationship between angular velocity and tangential velocity. What relationship is that? From v is equal to what? Omega what? Omega a. Or we can say omega r. Omega what? Capital R. You can call this equation number 2. Recall that your omega is given as what? 2 pi f. And that t is equal to 1 over f, and f is equal to what? 1 over t. So this particular omega can be written as what? Omega is equal to what? 2 pi times 1 all over t. Meaning your omega is equal to what? 2 pi over t. So we can call this equation number 3. So input equation number 3 into equation 2. And if you do that, what do you have? What do you have? If you do that, what do you have? If you do that, you have something like this. Your V is equal to what? 2 pi all 2 pi omega is 2 pi over t. 2 pi over t times radius r. You can call this was equation number 3. You can call this equation number 4. Equation number 4. So we have harvested the number of equations that we need in this derivation. Equation number 4 is one of them. We have V is equal to 2 pi r all over t. This is equation number 4. Yes, equation number 4. And the last one is from Newton's, which is supposed to be the first one, is from F is equal to G MEN all over R squared. All over R squared. You can call this equation number 5. Now, I'm going to clean this. Screenshot the diagram. I'm going to clean this. I told you about the physics of cut and join. We are going to equate equation 1 with equation number 5. If we do that, this is what we have. They both have the same SI units and are used under the same condition. Both of them are used for circular motion and also motion under gravity. So we have our mv square over r is equal to what? Is equal to g MEN over what? R squared. Yes, but v is going to be what? 2 pi r over t. So this implies that I want to simplify it further. Let's move down. If we cross multiply, we have mv squared r squared is equal to g MEN r. If we divide both sides by n r squared, we have n r squared. This will go, this will go, this will go, this will go, and we're left with one of this will go, and this will go, this will also go. Yes, this will go, this will go, this will go, and you're left with 1 r down here. So your v squared is given to be what? GME all over r. But what? But our v is equal to this. So now we can write but v is equal to what? 2 pi r all over what? Over t. So we are going to clean this side and rewrite. From v squared is equal to GME all over r. We are substituting this in place of v. So we have 2 pi r over t. You square this, is equal to what? GME over r. If you square this, you're going to have this and this, you have 4. This and this, you have pi squared. This and this square, this square, you have r squared. You have t squared. If you clear this bracket, it's equal to what? GME over r. If we cross multiply, we are having t squared GME is equal to what? This time, T square, we're having T square GME is equal to what? Is equal to 4 pi R square times what? R. This will give us R cube. So now we're having T square GME is equal to what? 4 pi square R cube. So we're going to make T square the subject of the formula. Can you see that? So if we do that, we are going to have something like this. To do that, we're having T square GME is equal to what? 4 pi square R cube. So we divide both sides now by GME. Do that, this will cancel this, this will cancel this. Therefore, T square is equal to what? 4 pi square divide by GME times R cube. And this is what we call Kepler's law. Kepler's law. This is the law. The square root of the period of oscillation of all planetary body, the square root of the period of revolution of all planetary body is directly proportional to the cube of their mean distance. So your T square is directly proportional to what? R cube. Removing this sign of proportionality, we say that T square is equal to what? Is equal to what? 4 pi square over GME times what? R cube. In your physics textbook, in your useful physics textbook, this is the only thing you have. You don't have this with you. And so we have succeeded in deriving Kepler's law of planetary body. And if you do, should you be asked this in your examination, this is how to go about it. To this, we have come to the end of today's online lesson, online video. Please promote this channel, share these videos. Those who are still in secondary school that need this knowledge, share to them, subscribe to this channel, like, comment. I welcome every form of criticism because it makes me grow. Bye-bye. God bless you.